Okay. So last time, whatever we read, have you gone through, or you need some kind of revision?
हेलो
Yeah.
या सुनाई नहीं दिया था वॉइस वॉइस करते हैं
Okay. So last time what we went through was we were calculating the gradients. Um, we were mentioning that this particular variable B and W, which is the two variables we want to calculate the gradient. We were mentioning that the grad the flag as true. We were making the grad request grad as true, and explicitly mentioning that we need to calculate the gradient of these two variables. So here we initialize the B variable, here we initialize the W variable, and then in the in the declaration itself we were making requires grad equal to true. So it was making the grad true. So that means what? We don't have to manually by hand calculate the partial differentiation and apply it in the code here, which it will be taken care automatically. So that is the main purpose of this requires grad. Okay. But after that, we saw one thing that there is an auto grad feature in Python, right? To use the benefit of partial derivatives, chain rule, everything, we have to use the differentiation automatic differentiation package of Python, PyTorch. And this automatic differentiation package is called AutoGrad, which has a method called backward, and it will be calling the computing the gradients from the starting point in a iterative manner, like which will be applying the chain rule. So that is what we knew yesterday in the last class. So here it was like that: y hat is equal to this value, then error is y hat minus y tensor, loss is this much, and now in the previous part, we were calculating B grad and W grad separately, but here with just loss dot backward, it automatically calculates the B grad and W grad. Okay. Now you may ask that I am calling backward on loss, but how does it calculate the B grad and W grad? It does it because loss is dependent on error. Error is dependent on y hat, and y hat is dependent on B and W. And B and W are in this entire chain of variables. B and W are the variables which has the required grad flag as true. So automatically, which it will see that this variable is dependent on a list of variables, and out of those list of variables, whichever is required grad is true, it will automatically calculate its gradient. Okay, and this is the dynamic computation graph. We'll come to that slowly. How we will know. Okay. So now if you can see here, error requires grad, y hat requires grad, b requires grad, w requires grad. All of them are true because all of them are dependent on each other. B and w is dependent on y hat is dependent on error. So all of them by default gradient becomes required gradient becomes true, while x and y tensor are not gradient true because they are not directly dependent on b and w. That's why their gradient is false. Okay. Now we saw that we can directly print the gradient by b dot grad and w dot grad, which is very easy, and straight away we can do it. But we saw one thing that if I print this, so this will be in a loop, right? This part will be in a loop, right? In every epoch, this will be in a loop, right? So what will happen is that we'll see that every time we print b dot grad w dot grad, this value will be double: -3 -1, then -6 -3, then -12 -6, and keep on increasing. But why is this happening? This is happening because of a accumulating gradient problem. Okay, this is the last thing we saw in the last class. Accumulating gradient problem. What is this accumulating gradient problem? This is a very beautiful thing to understand. Is that mostly what happens in data science? we need a lot of data, right? And we train on a very large data, and it is so large that even the batch gradient batch gradient policy, where we are not using the entire data to calculate the gradients at the same time, that batch itself also is very big. Okay, the batch itself, the batch may be also very big to fit in memory card of the graphics card, right? So what happens is that to solve this, the batch is again divided into sub batch, so called sub mini batches. Okay, so batch is divided into sub mini batch, and then it is calculated, gradients are calculated for the sub mini batches. But to the user, it seems like they are calculating only the batch gradient. Okay, but to the user is not knowing that I am actually calculating multiple sub mini batches inside. User sees that only the gradient of the batch is calculated. But how does the system or the compiler take care about it? It actually accumulates the gradient of these mini batches, keeps on adding them, and finally delivers this as the final gradient of this batch. That is the only reason that the gradients by default get accumulated. Okay, this is a feature from PyTorch. Okay, so this feature is a good feature actually, but for this case where we have a very small data, this case it is not helpful because it is accumulating the gradients, right? So what we have to do, we have to simply call dot zero. Okay, this function we have to call b.grad.0 w.grad.0. What it will do, it will zero out the gradients. You see, whatever the gradient value was there, it is zeroed out now. Okay. So so now
Uh, we have to call this dot zero function each time before calculating the gradient, right?
yes, I will show you where you have to call inside the loop.
Okay, okay.
So now what we will do is we will call the backward method. Okay, and if you remember the backward method, so the backward was here. It was the method for the loss. Okay, the loss dot backward. Now backward method is activated only when uh, we are making some of the variables dot required grad as true. So in that case, grad, we don't need to calculate B grad, W grad separately. We will just calculate the loss grad directly. So if I'm calculating the loss grad directly, then how do I do B grad dot zero and W grad dot zero? Because I am not calculating B grad, W grad separately, right? I am calculating the gradient in total. So how I will do in how I will zero out the gradient of individual elements? I will simply call I'll I'll simply call the zero underscore method. Okay, zero underscore method. So that is here you can see here. So here is we are calculating the y hat error loss dot backward, and now we do this. I'll tell what is this, but for now, just keep in mind that b.grad.0 underscore w.grad.0 underscore. Okay. So when I am doing loss dot backward, it is calculating the gradients. Okay. So here it is written, when you are doing loss dot backward, no need to calculate manually the gradients. It is automatically calculating the gradients. And here you are zeroing out the gradient before after the updation, right? So you asked, right, where we have to zero out the gradient. We have to zero out the gradient after updating the parameters. So ultimately what we are looking for, we are looking for the optimal B and W value for a linear regression, right? That is our goal. Our learnable parameters are B and W, right? So our in every loop we will update B and W. After B and W are updated by the current grad value, we have to zero them out. Otherwise, what will happen in the next loop is this B dot grad will be double. in the third loop, it will be triple. So our gradient calculation will not be correct. Actually, our updation will not be correct. Sorry. So for that reason, we will have to zero them out, and this is the way we do it zero. Okay. Now here is an interesting thing. You see, you could have said me that I can straight away update the learnable parameters in this way, because this is the most effective means of updating the learnable parameter, which is b is the new value, old value b minus learning rate into gradient. This is how we have been doing in the earlier when we are doing manual calculation of b grad and w grad. We were doing it this way. But why, if I do it in this way this time, why it will give an error as non-type object has no attribute 0? It will give an error. Why? It is because when you are doing this line, you are updating the value of b, right? You are updating the value of b from, you are subtracting this much from the old b, and that value you are updating to b. In this updation procedure, in this equal to procedure, the grad is lost. The grad flag gets lost. It gets overwritten and lost. Since it gets overwritten and lost, so 0 is also not applicable anymore. 0 is only applicable to variables which has grad flag, right? If the variable has no grad flag, then what is the point of making it 0, right? So when you do such kind of updation, then our b parameter loses the grad flag, and that is the reason this is not possible. Second is, you can tell that I will make in place assignment, right? So this is a little more better way of doing b minus equal to this one. So this is in place assignment, but this will also cause an error because there is a reason behind it, which I will tell little later. It is due to the dynamic computation of graph. It will give an error. Okay. In the third attempt, so for that, what we have to do is we have to call this with torch no grad. Okay. Then you have to call this in place assignment operator, and that is the correct way to update the dependent or learnable parameters. This is the correct way to update the learnable parameters. Now, what does torch.nograd do? I will tell you. What does torch.nograd do? But this is the final program that we are looking at, calculating the y-hat value, error, loss, backward, update value, zero out the gradient, and again continue the continue the loop. Okay. Okay. So this is what we read now. Okay. Now we will know about dynamic computation graph. This is very important. Dynamic computation graph is very interesting to see also. Okay. So for this, you need a package called PyTorch Viz. Okay. So apart from PyTorch, you have to have a PyTorch Viz package, which you can straight away install using pip install, which is easy. Okay. So what happens with this is that here you see the same thing we have done, but we are making make dot y hat, right? So y hat is this one, error is this one, loss is this one, and I am trying to see the graph of y hat. Y hat is this parameter. Okay. And what is y hat? Y hat is the combination of one variable b, which requires a gradient, plus another variable w, which requires a gradient, multiplied with another tensor. Just a minute. Okay. So now, let us see what is the output of this. Okay, you see the output, it looks something like this. Okay, now this is an interesting output. You have to understand this output. This is very important. So there are three kinds of boxes in here: blue box, gray box, green box. Okay, so green box is the point from where we are calculating the dot loss dot backward function. If you remember, this loss dot backward, okay, this is the point from where we are calling the backward method. Okay, what was backward doing? Backward was calculating gradients, right? We didn't use this manual gradient calculation of gradients, it was automatically calculating. So backward is calculating the gradients. Okay, so now consider this green point as the point from where the gradients has to be calculated. Okay, now I want to calculate the gradient of y hat. Okay, good, I can calculate. Now what is y hat? Y hat is b plus wx. Okay, good. Now this is a summation operation. Okay, sum operation, and I will bring b from here. Okay, and I will bring wx from here, and I will add them both to become b plus wx. Now this b is coming from here, which is blue in color. Blue means this b variable requires gradient calculation. Okay, and here we see wx, and if I see, I am seeing only w. I am not seeing a arrow for x. Ideally, you should think, right? If b is coming here, w is coming here, then where is x? X should also come in this graph, right? But x will not come in this graph because x is an independent tensor which does not require gradient calculation. The requires grad flag is false for x. Okay. Whereas the required grad flag is true for b and w. So whichever term or whichever arithmetic operation is involving b and w directly, they will come in the graph, not anybody else. Okay, so that is how it is. This graph is formed. This is what is written here. Okay, and if he did a simple change here, he removed the required grad flag from b. He removed the required grad from b and did the same thing again. You see here, now b is removed from the graph. Okay, so this is very, very important for us to understand how gradient is calculated in the chain rule and back preparation. How individual variables, how arithmetic operations, we can have a loss function very complicated, right? So if we want to know how is which all variables actually gradient computation is happening, all we can know through this make dot function in PyTorch viz. Okay, this is a very important good feature. Another one is tensor board through using from TensorFlow. I will also tell that. That is also very important. Okay, now here you see they made it more complicated. Now loss is they are telling that if loss is greater than 0, then take a different path. Now why is this one? Don't think about this logic. This makes no sense. This is for understanding only. He's telling that we can calculate loss in two ways. One is loss from here to here. Okay, this is one method. Another method is loss from here through here to here. Right? If loss is by greater than 0, then it will follow this path. If it is less than 0 or equal to 0, it will follow this path. So will this logic be also captured in the torch viz? Let us see. So you see here. So here, if you see, so we have, here is the branching, right? So branching has happened. That means there is a if statement. This branch is when if loss is less than or equal to 0.
Okay.
And this branch is when loss is greater than 0. So some extra steps are added here. Okay.
Okay. Means whatever change we do to the variable with grad equal to true will be captured in this graph.
Yes. Yes. Yes.
Okay.
And it is telling that it will even capture the if conditions also.
Okay.
This is very, very important for understanding our model structure, how gradients are being calculated, how those things are being done, everything it is taking into place. Okay. Okay. Now I'll come to optimizer. We all know about optimizer theoretically. I am assuming that optimizer, what is an optimizer, we already know, but we will see how can we use that optimizer in PyTorch. Okay. Now, until now, what optimizer we read, it was gradient descent optimizer, right? Whatever we read, it was simple. Take all the points, calculate the loss, calculate the gradient, update the learnable parameters, and repeat itself. So this is gradient descent optimizer, right? But as you all know, this is highly impractical because multiple reasons. One is we will have millions of data sets, so we cannot possibly calculate the loss for all the data points at the same time, and it is going to be very slow, right? So for this reason, there are multiple different types of optimizers like SGD, RMS prop, Adam. Okay, out of which SGD is the most basic and Adam is the most popular. Okay. If we want to read about what are these optimizers, how they work, then you can read it separately in YouTube. Which is not covered in this course. I will just tell how to use the optimizers, which optimizers to use for which case. That one we have to see from outside. Okay. Now this is a very important animation you see here. They have made here. So this animation shows that from a random point, if I start all the gradient descent, then you see how different optimizers reach to the minima. So the star is the minima. Okay, the star point is the minima, and all of them are trying to reach the minima. As you can see, ADA delta reached first. Then ADA grad reached second, then RMS prop reached third, and so on. NAG and momentum, and SGD is worst. It is not reached until now also. Okay. So this is a good animation of you understanding. You can also draw these animations. You know right now how to calculate everything. So you can also do contour lines and calculate and see the graph of which optimizer is working best for your model. Okay. Okay. I will give this link also if you want to know more about this. So here is a library. Convolution neural network for visual recognitions. So this is the course complete. Course of Stanford.
So it's like online course, no?
Yeah, online course.
Okay.
Now, step and zero grade. This is important. So now we are telling that we will not use, we will omit many steps now. We will omit many steps and we will use the optimizer. Okay. So how we will, what steps we will omit and how we will use the optimizer in place of it. Okay. That is what we have to know. First is we have to define the optimizer. Okay. So the optimizer is optim.sgd. You have to give which are the dependent learnable parameters, B and W, and what is the learning rate. Obviously, why I have to give B and W? Because I have to know for which I want to calculate the gradient, right? So I already know here I want to calculate the gradient of the y-intercept and the slope. So B and W, I know these are the learnable parameters. So what I have to do, I have to give them as into the SGD as learnable parameters. If you are designing a polynomial regression, then you will give more than two here, 3, 4, 5 variables you will give. If you have more than two variables which are helping you determine the regression line, then you will give more than two variables here. Okay. So now we don't need to zero the gradients one by one anymore. So b dot grad zero underscore w.grad.0 underscore. We were doing it separately, right? We just need to call zero grad method on the entire optimizer. Okay, and it will do the zero gradient thing. Easy. Okay, so this is the code here. So this is our y hat. This is our error. This is our loss dot backward straight gradients calculated. Then this is the dot step method. So what did dot step do? Dot step omitted these three lines. Okay, it omitted these three lines. One is no grad, and then this updation of the learnable parameters. This is the three steps. It completely engulfed in this one line, and then separately we were doing zeroing out the gradients. But here we so if you have, say, here we have only B and W. Suppose you have a polynomial regression and we have, say, 20 parameters, learnable parameters, then zero grad will do the zeroing out of all the 20 parameters at the same time. Okay, so this is the how we will use optimizer. The same things it will come here. Now loss, how do we tackle the loss computation? Very easy. Like optimizer, there are many loss functions ready-made. If there is no ready-made loss function, you can write your own custom loss function also and use it. So here we are using the loss function, MSC loss function, which is inside the NN package. NN package is inside the torch package. So and you have to give the reduction method, whether you want to calculate the mean or you want to do the sum or what you want to do. So what does the loss function take? It takes predictions, and this order is very important. You have to remember this. Although it is not important for MSc, but for likelihood loss, log likelihood loss function that I will tell you in logistic regression in the future classes. For that, the ordering is very important. Okay, so that is why PyTorch says that irrespective of whether your order is important or not, you always give predictions first, labels second. Okay, so this discipline you have to maintain so that you don't face unnecessary problem. Because what will happen if you change this order in logistic regression, you will not get any error. The system will not give any error, but it will give you wrong loss values. Okay, so you will never know that what mistake you are doing. So if it is throwing an error, then what at least you will know that okay, this is the problem I had. So that is why it is best way is that keep always prediction first, level second. Okay. Yeah, so it is written here, reduction or sum, whatever type of methods you can use for the MSc. Higher order function, I will explain it later on. Higher order, what is the higher order function? Okay. So here, let us see what are the finally it looks like. So we have optimizer, we have a loss function, and then what all we have to calculate y hat. Now, no more calculating loss manually. Straight away, we can calculate loss, prediction, labels, loss, and loss dot backward, optimizer dot step, optimizer dot zero grad. So you see, we are making the epoch smaller and smaller. Epoch code is becoming smaller. We started with all things done from scratch manually, and then we are slowly making things compact and compact. Okay, then we will see how we will introduce object-oriented methodology here, how we will use function decorators to make it more easier. So all those things will come slowly. Okay, so this is our loss. And finally, this is very important. Now, if you want to, what if we wanted to have it as an umpire? So loss is what now? A tensor. Okay. So if you print B and W, this is the B and W. I can print loss also. If I print loss, then it will tell that this is the loss and it is in device CUDA 0. Okay. So, but I want to get the loss into an umpire. What I will do, I have to first bring the loss to the CPU, then convert it into numpy, because in the GPU there is no numpy. Okay, but still there is a problem, because this loss is dependent on the gradient graph, the dynamic gradient graph that I just showed you some few minutes ago. That means what? The graph is there. Loss is dependent on B and W. So loss is part of that graph. And since loss is part of that graph, I cannot straight away pull it and bring it to the CPU memory. What I have to do, I have to call detach first. Means detach the loss variable from the graph, bring it to the CPU, then convert it into a numpy array. Okay. So this ordering is important. Detach CPU numpy. This is the way it happens. Now, every time if I have to print the value of a loss variable or get something from GPU memory to the CPU, so much work has to be done. No. What can be done? We can easily do it in one step called loss.item or loss.toList. Okay. For tensors with a single element, it is .item. .toList. Otherwise, if it is a single scalar, then it will return a single scalar. If loss will return a list of values, you can have different kinds of loss, right? So KL divergence and others will have different kinds of loss, right? So those will become different. So loss.item or loss.toList. So if you are sure that your loss is a single scalar, then .item you do. If you think that it is an array of numbers, then you do toList. ToList can also be used for an array of single number. In that case, it will return a scalar. Okay. So this is loss function until now. Okay. Now what is remaining? We read about optimizers. We read about loss functions. We read about gradient auto grad feature. Now the main important thing is remaining is the model class. Okay. So in PyTorch, a model is represented by a regular Python class that inherits from the module class. Okay. The module class is the base class for every model. Okay. So here he is telling that I'm assuming that you are acquainted with the classes, constructors, and all these things of object-oriented concepts. If you are not, then you have to tell me. But I assume that you already know this.
Yes.
Yeah. So here, the most fundamental methods of a model class needs to implement are the init method. Okay. The init is like the constructor method. Okay. It defines the parts that makes the model, in our case, two parameters B and W. So it tells us that this model, what are the learnable parameters of this model? In our case, it's a linear regression. So slope and y-intercept are the two learnable parameters. So we will keep those two parameters in init. Okay. You are not limited to defining parameters though. Models can contain other models as their attributes as well. So you can usually nest them. Nesting of models is also possible. Okay. So it's not necessarily that only a model contains some parameters. A model can contain another model also. This is called nesting of models. And in that case, you have to use the super call of the constructor, so that the parent class constructor or init is called before the derived class. Okay. Now we have a forward method. Okay, inside the module So all these methods are what inherited from the module class, right? So suppose you are defining a model like class linear regression colon module. So module has forward method, so that forward method by default comes into your class as well, right? So what happens? It performs the actual computation. That is, it computes the prediction given the input x. Okay, so this is prediction. This forward function calls the prediction. Okay, it may seem weird, but whenever you using a model using your model to make predictions, you should not call forward method. Although it's by definition it is telling that the forward method is the one which makes the prediction, but you should not call the forward method explicitly from your model class model object to get the prediction. You should call the whole model instead, like this model x, not model dot forward x. Okay, the reason is the call to the whole model involves extra steps, namely handling forward and backward hooks. If you don't use hooks, I'll tell you what are hooks. Okay, so if you don't use this method of calling the prediction, then what will if you do model dot forward x, then what will happen? You will lose the opportunity to call handling forward and backward hooks, which can be implemented when you call in this manner. Okay, I will tell what are hooks in later part. Okay, let's see a sample model now. Okay, now this is my sample model, manual linear regression. It is inherited from the module class. First line is super init because I have a super class, I have a base class. Okay, now obviously B and W are my learnable parameters. So I have to put them here. Now here is a difference you can see. I have put them inside nn.parameter class. I have put them inside the nn.parameter class. Why nn.parameter? Okay. Why I'm wrapping them with the nn parameter? I'll tell you. Okay. Now the forward function, what it does, it calculates the prediction. Simple. Prediction was what? Self.b, self.w into x. This was the prediction. What is prediction? For our case, it was the y hat, right? If you remember, y hat is equal to, we were doing b plus wx, right? The same thing will be here. Okay. Now parameters. In the init method, we defined our parameters b and w using the parameter class to tell PyTorch that these tensors, which are attributes of the manual regression class, should be considered parameters of the model the class represents. So we are explicitly telling the class here that this is a model. Okay, this is a model, PyTorch model, and these b and w are parameters of that model. Parameters means learnable parameters of the model. Okay, where x and y are not learnable parameters, but b and w are learnable parameters, which requires gradient as true. Okay.
Yeah, I had a doubt that when we put that requires grad equal to true, it is by default the learnable parameter because it's requiring gradient descent in that.
Yes, there is also some other benefit also using this. I'll tell you.
Okay.
Okay. Why should we care about that? By doing so, we can use our models parameters methods to iterate over all models parameters, including parameters of nested models. See, what is the importance here? If I make a dummy model of my manual regression and I just do dummy.parameters, it will give me all the list of parameters, the learnable parameters of that model. So you got it now. If I have not done nn.parameter, yes, true. I am telling that it requires grad is true. But can I get all the learnable parameters of my model in a single line? No.
No.
I will only get if I make those variables wrapped up in a parameter class. So when I do that, when I do dummy.parameters, it will give me the list of all the tensors which are learnable parameters. Apart from dot parameters, there is another method which is very, very important called state dictionary. Okay, this tells that this gets you a dictionary, tells that what is the parameter name and what is its value. So you can, at any point of training your model, you can check what is the state dictionary of your model. And it is very, very important in maintaining. You want to see that your how learning is going on, whether it is the parameters are updating themselves or not, whether they are stuck, whether they are progressing or not. All these things you can do by calling the state dict method. Okay, the state dict method of a given model is simply a Python dictionary that maps each corresponding tensor, but only learnable parameters are included. Okay, as its purpose is to keep track of parameters that are going to be updated by the optimizer. Okay, so whatever parameters are learnable, that will be updated by the optimizer. That one we already know, right? Because that require grad is true for all the learnable parameters. By the way, optimizer itself has a state dict too. Okay, so optimizer itself has a state dict too, which keeps a lot of information, but this is out of the scope now. We don't want to know about this. Okay, we need to send our model to the same device where the data is. This is obvious, right? If we have our x and y tensors in the x, y, and b and w, no, x, y tensor is in the GPU. Model has b and w tensor. So obviously I cannot keep the model in the CPU and XY in the GPU and then calculate all these things. I have to send my model to the GPU memory. Okay, so it is very easy to do. You just do two device. Okay, this transfers your model to the GPU. So now you can access X and Y tensors very easily. Okay, so forward pass, as I said, do not call model.forwardx. Okay, we have to call model x. Okay, so now let's see how our method has improved. We are creating a model, we are creating an optimizer, we're creating a loss function, and now this is a strange looking thing. We'll see what that is. Okay, so here you see y hat is equal to model x tensor. What did it replace? Here it was y hat is equal to b plus w into x was there, right? In this place of b plus wx, I am replacing that with model x tensor, x trend tensor. Okay, so that means it will call the forward method of the model, the prediction method of the model. Okay, so no more manual prediction. Okay, now why this is required, I'll tell you. Okay, after that, same loss, calculate the loss direct, loss backward, optimizer grad. And now we can straight away do model.state dictionary. We don't have to do model.b, model.w. We don't have to take care of that. We will do model.state dict and we will see all the variables, how they are doing. Okay, we get the output here. Okay, now train. I hope you noticed, yeah, what is this train thing for? In PyTorch, models have a train method which somewhat disappointingly does not perform training step. You may think that this is here to make a training step. Okay, no, this is not here to do a training step. It is only purposed to set the model to training mode. Okay, why is it important? Some model may use mechanisms like dropout, for instance, which have distinct behavior during training and evaluation. So this one, I hope you know, the dropout is only happens during training phase. Dropout doesn't happen during prediction phase. Okay, if you have a deep neural network and I have added dropout layers, dropouts will be only applicable during training phase. It will not be applicable in the prediction phase. So that is why you explicitly tell that my model is now in training mode or prediction mode. Okay, or it will be eval mode actually. Model.eval. We will see during the evaluation.
Yeah. So like, why do we call it inside the loop? Like, can't we call it outside the loop and then run the training loop?
I will also show that, because inside the loop we will do batch training, batch evaluation, batch training, batch evaluation. So every batch we train, then we'll do we'll do a set of evaluation.
Okay,
So,
okay, got it.
Yeah. It's a good practice to call model.train in the training. It is also possible to set a model dot to evaluation mode. I'll tell you where we use this. Okay. Now nested models. Yeah, this is important. In our model, we manually created two parameters to perform a linear regression. What if instead of defining individual parameters, we use PyTorch linear model directly? Okay. So here we created our own class, manual linear regression, right? So what if there is already a class built for that in NN package, linear regression? What it tells? It tells that input feature is 1, output feature is 1, and bias is true. This is the model. Straight away we can do this, right? Input means X, output means Y, and bias is true. Okay. Now, can I say the dict, state dict? Yeah, but it is no more B and W. It is W and weight and bias now. Okay. So because this is we did not explicitly do self.b or self.w here, right? We did bias true and out features in features as well. Okay. So in features become my weight and bias become my bias. Okay. So our former parameter B is the bias now, and our former parameter W is the weight now. Okay. Your values will be different since I haven't set up. Every time you print the state dictionary, it will give different values because we do not have the random seed set here. Okay. Now let's use PyTorch linear model as an attribute on our own, thus creating a nested model. Okay. So as I was telling about nested model, here we will do a nested model. So instead of giving self.b, self.w, I will do self.linear. Okay. And I will use the existing function here. So if I am using this, then here what I will do, obviously, I don't need to call y hat is equal to that. Okay. I will straight away call model name and the input parameter, right? You remember we don't have linear model is also inherited from module class. So linear model also will have a forward method. So if I call the method model name and x, then it will call its forward method where it will be doing linear regression. It will be calling the prediction method, right? So yeah. So we are not calling self.linear.forward.x. So we will only call the method model name. Now we, as usual, we can send the device to the CUDA. We can check the parameters. You see by default those parameters are that is true. The state dictionary you can see. Now it is a nested state dictionary. See, linear.weight, linear.bias. Okay. Why it is like this? Because my regressions dot state dictionary is telling that my regression dot state is telling I have one parameter which is linear. Then linear is telling that I have two parameters, weight and bias. So that's why I am getting the order as linear.weight, linear.bias. Now, if I put my my linear regression inside my my regression class, if I put this class object inside my regression class and I print the state dictionary, then what will happen? It will happen linear.linear.bias, linear.linear.weight. Okay. As many nesting you will do, that many nestings will happen here. Okay. Notice that both bias and weight got a prefix of attribute named linear from the self.linear method. Okay. So this is yeah. Sequential models will start to. This will be the entry of deep neurons. We'll start from here. Any questions you have?
No, not till now. Like, I just had like a doubt. Like, in like upper, there is a linear model which we are using, and then we want to use polynomial model upon that. Like first linear, then polynomial. Then in forward method, we would just call self.linear x and then self.polynomial x.
It all depends on you, how you want the prediction to happen.
Okay.
So you are defining a custom model class. In that custom model class, if you tell that I will do linear prediction first, then I will do a polynomial prediction, then it is your choice.
Okay.
Right. So you are doing a custom class. So you are borrowing PyTorch's existing models and defining your own custom class. So you can do anything you like.
Okay, got it.
Okay. Any other questions?
No.
Okay. 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 I'll upload this class in the YouTube then. Okay.
Okay.
Okay. Thank you.
Okay.